Hello everyone, my name is Patty Homan and the title of my capstone project is Thorium Reactors, the Future of Nuclear Energy. My teammates are Tim Gallagher and Tim Webb, and together we set out to research and evaluate the use of thorium-fueled nuclear reactors and their potential as a viable alternative to uranium-fueled reactors. Tim Gallagher is our team lead, and he's responsible for looking at the technical data on thorium fission and how it compares to uranium. He also focused on thorium use in molten salt reactors. I covered the history of experimental thorium reactors as well as the current state of research and development of thorium-fueled reactors. Tim Webb has the responsibility of evaluating the pros and cons of thorium reactors so that the three of us as a team could reach a consensus on whether thorium-fueled reactors are a viable alternative to uranium power plants. Since the history and current state of thorium research is my area, that is where I will focus this presentation, but I will also provide an overview of the technical data and the pros and cons of thorium-fueled reactors to support my opinion on thorium reactors. Since the 1950s, when research into nuclear power was really taking off, thorium has been in the mix as an alternative to uranium. Thorium is 3 to 4 times more abundant in the earth than uranium and is widely dispersed geographically. Certain countries, India in particular, have large thorium deposits that make it an attractive alternative to uranium. The challenge with thorium, however, is that thorium is a fertile material rather than a fissile material. This means that thorium must first absorb a thermal neutron before it can decay to a fissile fissionable material, which is uranium-233. Consequently, in order to utilize thorium as a fuel in nuclear reactors, you need a seed fuel that produces neutrons and can maintain the fission chain reaction. Uranium-235, by contrast, is fissile. Uranium-235, however, is only 0.7% of naturally occurring uranium. The rest is fertile uranium-238, so uranium fuel must first be enriched to provide a viable fissile fuel in uranium-fueled reactors. Although uranium ultimately became the nuclear fuel of choice, research into the use of thorium continued because of concerns about long-term availability of uranium. There are generally two types of thorium fuels: solid thorium that's retrofitted into existing reactor designs like light water reactors, heavy water reactors, and high-temperature gas reactors, and liquid fuel salts utilized in molten salt reactors. In light water reactors, we basically see fuel rod assemblies of thorium oxide pellets inserted into the core in various configurations with some seed fuel rods containing uranium or plutonium oxides that establish the fission chain reaction. In high-temperature gas reactors, the fuel is also solid. Pellets of thorium and uranium or plutonium oxides are embedded in a graphite moderator. The graphite moderator can be in the form of graphite blocks inserted into the core or graphite spheres in pebble bed reactors. The more advanced and interesting option involves molten thorium salts, where the thorium fuel is dissolved in fluoride salt. Another liquid salt is used as a coolant. As the fuel salts are cycled through the core, they are also being run through a chemical processing plant to remove fission products. Historically, research into the use of thorium as a fuel has largely focused on retrofitting available reactor designs to accommodate thorium fuel. Experimental light water reactors, heavy water reactors, and high-temperature gas reactors all yielded important experimental data and operational information. Pressurized water reactors at Indian Point, New York, and Shippingport, Pennsylvania operated in the 60s and 70s and successfully demonstrated the ability of thorium fuel to breed uranium-233. In addition, the Shippingport reactor also demonstrated that a conventional light water reactor could be retrofitted to a thorium and uranium breeder reactor with minimal changes in design and operation of the plant, making it economically feasible to convert uranium reactors. Boiling water reactors at 2 locations successfully demonstrated the use of uranium and thorium oxide fuels in these light water reactors. The Borax 4 reactor at the Argonne National Lab in Idaho operated from 1956 to 1958 and was an experimental reactor used to test high thermal capacity uranium-thorium oxide fuel. The Elk River boiling water reactor, which operated in the mid-60s, also used a uranium-thorium fuel. The boiling water reactor in Lingen, Germany, began operation in 1968 and was terminated in 1973, and it successfully demonstrated the use of a test fuel of thorium with plutonium oxide rather than uranium. Pressurized heavy water reactors utilize heavy water as a moderator because it absorbs fewer neutrons than normal water, leaving the neutrons available for fission reactions. Both India and Canada have constructed experimental reactors to perform irradiation tests on thorium fuel in heavy water reactors. In Canada, thorium-based fuels have been designed and tested for their CANDU pressurized heavy water reactors. Mixed thorium and uranium oxide fuels and thorium-plutonium oxides have also been tested. Thorium fuels have been successfully demonstrated in high-temperature helium gas-cooled reactors as well, in the United States, the UK, Germany, Russia, and Japan. With its high melting point and resistance to radiation damage, thorium fuel is well suited to use in high-temperature gas reactors. The 20-megawatt Dragon experimental reactor in the UK, which operated from 1964 to 1975, was the first high-temperature gas reactor and was designed to test irradiation of fuels and fuel elements. The Peach Bottom reactor was a 40-megawatt high-temperature gas reactor demonstration plant in Pennsylvania that operated between 1966 and 1974. Operation of Peach Bottom resulted in changes in the manufacture of fuel kernels, the success of which paved the way for a large-scale thorium-fueled high-temperature gas reactor at Fort St. Vrain. Fort St. Vrain was a 330-megawatt commercial nuclear power plant owned and operated by the Public Service of Colorado. The AVR and THTR high-temperature gas reactors in Germany, by contrast, were pebble bed reactors. The German AVR reactor was an experimental reactor that operated successfully from 1967 to 1988 and utilized a variety of fuel. A significant accomplishment of this reactor was a safety test in 1970 that demonstrated the inherent safety of pebble bed reactors. The German THTR reactor was a commercial reactor that operated until 1989 and was shut down over financial uncertainties. The Chinese and Russian modular high-temperature gas reactors are also experimental pebble bed reactors. The molten salt reactor experiment at the Oak Ridge National Laboratory was designed to investigate the feasibility of a molten salt reactor. The initial interest in liquid-fueled reactors originated from the idea of fueling long-range bomber aircraft. The molten salt reactor experiment was designed in the early 60s and began full operation in 1965. While it used uranium fuel, it was designed to simulate a liquid fluoride thorium reactor. Rather than the thorium-fertile blanket, neutron tests were conducted to validate the process. It was the first reactor in the world to operate with uranium-233 as fuel. In total, it operated for 4 years and provided valuable experimental data that, with further research into chemical processes, supported the concept of a single-fluid breeder reactor combining fissile uranium and plutonium with fertile thorium fuels. So, uranium is a fissile material, and it's used successfully as a fuel in commercial nuclear reactors. Why the renewed interest in thorium-fueled reactors? Well, a growing worldwide commitment to reducing greenhouse emissions is causing a new look at nuclear energy in general, and recent concerns about proliferation resistance, spent waste disposal, and a concern for operational safety are driving some to pursue thorium-fueled reactors. To put it simply, thorium-fueled reactors offer an opportunity to generate energy without carbon emissions, while also addressing concerns about nuclear proliferation, spent waste disposal, and safety associated with uranium reactors. Thorium is more naturally abundant than uranium and has higher efficiency in breeding fissile material in thermal reactors. Burning thorium fuel does not produce plutonium, and in fact they can burn plutonium from spent fuel. This means no plutonium which could be utilized for weapons and no plutonium to dispose. Low production of transuranics, the long-lived radionuclides, means lower long-term radiotoxicity, which alleviates some of the disposal issues of spent nuclear waste. Higher burnup produces less waste overall. Thorium oxide is also more stable than uranium oxides, making them safer for long-term storage and disposal. Inherent safety advantages in practice with thorium as opposed to uranium include the high negative void coefficient, which means better control, particularly in light water reactors and heavy water reactors. Better thermal properties, particularly a higher melting point, so there isn't an issue with fuel cell deformation, cracking, thermal expansion. Makes thorium fuel have fewer issues than uranium fuel. And when thorium is utilized in molten salt reactors, there are a number of inherent safety benefits, including that molten salt reactors operate at atmospheric pressure with a high boiling point, so you don't have explosive issues leading to catastrophic failure, as in light water reactors like Chernobyl. In a molten salt reactor, you have a continuous removal of gaseous fission products, so you don't have issues with fission product gas leaks. Molten salt reactors have an air-cooled freeze plug below the core, which will melt and disappear in a situation of increased temperature, including loss of power. And when this occurs, the fuel will dump out of the bottom into a configuration that stops fission. You also have a high negative temperature reactivity coefficient, so that as temperature increases, reactivity decreases and shuts down fission. In addition to the safety features and the issues with disposal, some countries like India and Norway have extensive natural natural thorium resources that are driving their interest in developing thorium-fueled reactors. Current research and applications of thorium-fueled reactors is occurring on two parallel paths, which are the retrofitting of uranium-fueled reactors in the near term and the development of molten salt reactors in the long term. The countries most heavily invested in the short-term conversion of light water reactors and heavy water reactors are Norway, the US, India, Canada, and China. India, Canada, and China are all currently pursuing the use of thorium-fueled heavy water reactors. India in particular has vast thorium reserves, few uranium reserves, and an ever-increasing demand for power, which has led them to focus their nuclear program on thorium fuels. All nuclear power reactors in Canada are heavy water reactors, so Canada is at the forefront of investigating the use of thorium in heavy water reactors. Current heightened concerns about the safety of nuclear power plants, nuclear proliferation, and disposal issues with spent fuels, and a desire to reduce carbon emissions have led to a renewed interest in molten salt thorium-fueled reactors. China, the US, Russia, Japan have all had groups pursuing their development. China, as the largest producer of greenhouse gases in the world, is working to develop low-carbon energy sources to reduce their reliance on coal. This has led them to pursue the development of nuclear energy, including advanced molten salt reactors. Thor Energy in Norway and the Lightbridge Company in the US are actively pursuing the use of thorium fuels in light water reactors. Norway has substantial thorium reserves and dwindling fossil fuel resources, which led to the establishment of Thor Energy in 2006 to evaluate the use of Norway's thorium for fuel. The Lightbridge Corporation is a United States-based corporation that is working in collaboration with Russia to develop advanced thorium fuels for existing light water reactors, primarily for the disposition of reactor and weapons-grade plutonium. In the 1950s, India formulated a three-stage nuclear power plant that they continue to pursue today. The first stage of this concept is the construction of pressurized heavy water reactors to generate plutonium from uranium. The second stage is the construction of fast breeder reactors that utilize the plutonium generated in the pressurized heavy water reactors and fertile thorium material. The third stage is the construction of thorium-fueled heavy water breeder reactors that utilize the fissile uranium-233, which was generated in the pressurized heavy water reactors, and would create a fuel cycle of thorium breeding and uranium-233 burning. An alternative stage 3 proposed is a molten salt breeder reactors utilizing thorium fuel. Canada, in collaboration with China, is currently working on thorium fuels for use in CANDU pressurized heavy water reactors. Since all nuclear power reactors in Canada are the CANDU type, and CANDU reactors have also been built in India, China, Pakistan, Argentina, South Korea, and Romania, there are a significant number of countries that could take advantage of thorium fuels as an alternative to uranium in heavy water reactors. As mentioned above, safety and nuclear proliferation issues have driven a renewed interest in thorium-fueled molten salt reactors. These liquid-fueled thorium reactors, as they are known, are being actively pursued by several groups in the United States. One in particular is Transatomic, an MIT-based startup that has designed a molten salt reactor based on the Oak Ridge National Lab molten salt reactor that can utilize nuclear waste as fuel, as well as thorium. In January 2011, the China Academy of Sciences began research on a thorium-breeding molten salt reactor and has a 5-megawatt prototype reactor under construction at the Shanghai Institute of Applied Physics in collaboration with the Oak Ridge National Laboratory. The Chinese plan is to develop a demonstration pebble bed reactor with solid uranium and thorium fuel that is cooled with liquid fluoride salts. This will be followed by the development of a thorium-uranium liquid-fueled molten salt reactor with breeding of uranium-233. The decision to begin with a solid fuel and salt-cooled molten salt reactor was made because the technical difficulty is lower than a reactor with the fuel dissolved in the coolant, and so it is a logical first step in designing a molten salt reactor. In this presentation, I have discussed the numerous potential advantages of thorium-fueled reactors. Some of the disadvantages are listed here. There is a lack of experimental data, particularly with molten salt reactors. There is no proven fuel reprocessing to remove the uranium-233 that is produced and use it. There is, of course, the cost of initial investment, development, design, construction, and particularly licensing. And in addition, the non-proliferation and disposal advantages may be somewhat overstated. So, to conclude, thorium-fueled reactors, and molten salt reactors in particular, offer advantages in safety, non-proliferation, disposal, and efficiency, as well as a strategic option to supplement uranium resources. As the world moves towards reducing greenhouse emissions, nuclear energy may become more economically competitive, which will make pursuit of new reactor designs and alternative fuels more attractive. Additionally, China's active pursuit of molten salt reactors may provide the data and operational experience needed to drive other countries to move to thorium-fueled molten salt reactors as a logical replacement for aging reactors.